This is the first of a 5-part series on functions. Part 1 defines functions and provides some needed vocabulary. Part 2 considers notations used for functions and how to find function values for given inputs. Part 3 looks at algebraic operations of functions, adding, subtracting, multiplying, and dividing. It also suggests instances when the domains of functions need to be adjusted based on those algebraic operations. Part 4 looks at function composition, defining it and looking at composition both for values and for the general case. Part 5 formally defines a function inverse and provides a method for finding the inverse for a function. Examples of all material are worked through in each resource. Before we can consider functions, we have to look at the general case. A relation is any set of ordered pairs. Any collection of points creates a relation between the x values and the y values. An example of a relation would be the set of the points 1, 2, 3, 4, and 5, 78. When discussing relations, and eventually functions, it is important to have a bit of vocabulary. The domain is the set of all the inputs. It is all the x values that are used in the relation, which means it is all the numbers listed first in the ordered pairs. The range is the set of all the outputs. It is all the y values that we see in the relation, or all the numbers that are listed second in the ordered pairs. Let's look at some examples. Consider the relation 1, 2, 3, 4, and 5, 78. The domain is all the x values for the points, so the domain of this relation is the set 1, 3, and 5. The range is the set of all the y values. This means the range for our relation is the set 2, 4, and 78. Because a relation is just a set of points, we can also determine the domain and range if we are presented with a graph. For example, consider the curve shown on the graph to the right. The domain of the relation depicted in this graph are all the x values used in making the graph. The graph goes continuously from -4 to +4. Formally, we would say the domain of the relation is the set of all the x values such that -4 is less than or equal to x, less than or equal to 4. The range of the graph is the set of all the y values for the points that comprise the graph. In the y direction, the graph is continuous from 0 through +3. The formal notation would be that the range of the function is the set of all values y such that 0 is less than or equal to y and less than or equal to 3. We have talked about relations. So what exactly is a function? It is a special form of relation where every element of the domain is related to exactly one element of the range. This means that each input is paired with only one output number. Our initial example of a relation 1, 2, 3, 4, and 5, 78 is actually a function. However, the relation 1, 2, 3, 4, and 1, 78 is not a function. In the second relation, we have a problem. The input 1 is paired with two different y values. This means the relation does not get the special title, function. But what happens if the relation has a large number of ordered pairs? Or what if the relation is depicted as a graph? Luckily, there is an easier method for determining if a graphed relation is indeed a function. Look at the graph and consider any vertical line. For example, slide a piece of paper from the left to the right along the graph. If any vertical line intersects the graph more than once, the relation is not a function. Here we see a number of graphs that may or may not be functions. Let's use the vertical line test to determine which of these graphs actually are functions and which are merely relations. This graph in the upper left is indeed a function. There are no vertical lines possible that would intersect the graph more than once. However, this circular shape is not a function. If we consider the vertical line that was drawn, the graph is clearly intersected twice. Therefore, this relation does not get the special designation function. This V-shaped graph is a function. In fact, it is the graph of the absolute value function. This is not a function. The vertical line drawn intersects the graph more than once. However, if the previous graph is rotated 90 degrees, it is a function. No vertical line will intersect the graph more than once. Functions can only assume real, defined values. There are certain situations that result in constraints to the domain for certain functions. There are two situations to consider: division by zero, or taking the square root of a negative number. If either of these situations are possible, we must limit the domain of the function so that they do not happen. Let's look at a couple of examples. Suppose we want to find the domain for the function f of x equal to the quantity x squared plus 1 divided by the quantity 2x minus 5. Because we are dividing in the function, there is the potential for division by zero. We want to ensure that this does not happen. In other words, we want to make sure that 2x minus 5 does not equal 0. Solving, we need to constrain the domain so that x does not equal 5 halves. But what would be the domain of the function g of x equal to the square root of the quantity x minus 7? Because our function can only have real amounts, we want to make sure that we only take the square root of positive values. So we force what is underneath the radical, x minus 7, to be greater than or equal to 0. Which means that we have to force our domain to only be the x values greater than or equal to 7.